Hello, we are going to watch a video of a paper ball as it drops to the floor. We'll extract motion data from the video and construct models using Newton's second law and compare the predictions of the models with the observations. We'll discuss extracting the motion data from the video of the ball, and here is a summary from my analysis. The video was recorded at 50 frames per second, and the distance between two spots on the wall was used to calibrate the length scales in the video. The coordinate system was chosen with the origin at the center of the ball just before it was dropped. The y-axis was aligned such that the object moved in the minus y direction as it fell. Let's see the video now. Okay. From the analysis, we obtained the observed position of the object as a function of time shown in blue squares in a plot that we generated using a spreadsheet. The motion of the falling object is observed for a total duration of 0.44 seconds. Our object is located at the origin and it is at rest. It's moving so with zero velocity. Now we apply Newton's second law to construct the computer model to help understand and predict the observed motion. As you can see here, the slope of the line is not constant. The velocity is changing, so the changing in the velocity is non-zero. So F net is non-zero. There is at least one agent from the surrounding that's exerting an influence on the object. Earth exerts force, the weight force, on the object, so we start with a model that includes the weight force as the only force, and therefore F net equal to weight. Now we launch VPython and we specify the initial conditions. We specify the mass ball, which is 0.011, the ball's initial position, and the ball's initial velocity. Also time t equal 0 seconds at the start of our observation. Our time step delta t is small compared to the duration of the observations. We also need to provide some initialization for our interactions with modeling. For the weight, we needed to specify constant g to describe the magnitude of the weight force. We also need to define the axis unit vector j hat here, that we used to specify the direction of the weight force. Let's look at the loop. We need also to specify the non-zero net force of the surroundings of our system. We assume that F net is due to the gravitational force. Now let's run the program. The visualization seems correct and the plot looks reasonable. Let's compare the model predictions by plotting them on the same graph as the observations. Okay, as we can see, for time t small the predictions are doing a good job, but for time t larger our model predicts the object to fall further than what we observed. That means that there are more innervations on the system from the surroundings, which means the air exerts a force which is called drag force. We run again VPython. By adding this time the drag force here. Let's run program, and here is the correct code this time. As you can see, the drag force depends on the object's speed. First, the object is moving slowly, so the drag force has negligible magnitude. But as the object continues to speed up, the magnitude of the drag force becomes more significant. Now we compare the prediction of the ball with drag and weight to our observations. You see here the green line, which indicates our computer model with weight and drag, and the predictions are doing a great job. Now let's examine the velocity versus time predicted by our model with and without drag. As the speed of our object increases, the drag force acting on the object increases. At some speed, the drag force will equal the gravitational pull on the object. At this point, the object ceases to accelerate and continues falling at a constant speed, called terminal velocity. The velocity as a function of time for our object falling from a non-dense medium and released at zero velocity is roughly given by a function involving a hyperbolic tangent, as we can see here. Velocity asymptotically approaches a maximum value, which called, as we said, terminal velocity Vt. So, for this reason, none of our models can predict a terminal velocity because the duration of the free fall was small and the drag force wasn't equal to the weight force. Last, if our object was initially thrown downward, the terminal velocity wouldn't exist for the previous reasons.